Okay, welcome to part 3 of lecture 6. So the question we now want to ask is, when is the exponential mechanism useful, and how useful is it? So here's one thing we can prove. So it turns out that how useful the exponential mechanism is really depends a lot on the structure of the problem. And sometimes you can argue it's very useful, sometimes not. But there's sort of like a few very general statements we can make, and we're going to see one of them. So here's a useful, actually, sorry, before we get into proposition, remember just to, that what we want to do is compare to the maximum possible score we can have, right? So that Q max, we said Q max of X, that's the max over possible outcomes of the score for Y. And so what we want to understand is something about the distribution. Like, what is the distribution of Q max minus the score of the thing we output, right? So we run the exponential mechanism on X. And we want to sort of get our hands on the distribution of this sort of error, this type of error. Like, how far are we in the score space from producing something of the optimal score, right? So like, again, in our approval voting example, if we output this candidate here, then our error is sort of this distance between the score of the maximum, that would be Q max up here, and then down here would be like Q of the thing we output. Okay, so here's what we can prove. So if Y is finite, and let's say it has D possible values, so we'll just number them D 1 through D. Now, then we can say the following relatively nice statement, which is that if we look at, so the expectation, so here's what we say, the expectation over of Q max minus Q of Y. And this is over Y sampled from the output of the exponential mechanism. This is at most 2 delta over epsilon times some factor that scales very slowly with D. Okay, so the expected error we get scales with delta over epsilon, that we'd sort of expect, I think, and then this factor of D that is that grows pretty slowly, that is like only logarithmic in the number of things among which we're selecting. So this is a really useful statement. And just, I'll say more, I'm not quite done with the statement of the proposition, but just like, what should we be, comparing to? So compare this to what we get when we add, if we try to release all the noisy scores, then we're getting something more like D over epsilon in our error. Okay, and so what this is saying is that instead of getting something that grows linearly with the number of things we're selecting among, we get something that grows logarithmically. All right, so in fact, the proposition can actually be strengthened a little bit. We can actually prove the following stronger statement, that the probability over, y sampled from the same distribution. Okay, so the probability that this error exceeds 2 delta over epsilon times log of d plus t is at most e to the minus t, and this is true for all positive t. Okay, so for any number t, we get the following sort of nice statement, which is that the probability that the error gets like more than t above log of d times 2 delta over epsilon drops down exponentially with t. Okay, so once you pass this log, not only is the expectation just a little bit bigger than 2 delta log d over epsilon, but once you get past that, you have a very small probability of like seeing those outputs. Okay. So in particular, what this means is if there's a clear winner on in your selection problem, if there's one candidate, say in your election, which won by like a noticeable margin, it won by more than something logarithmic in the number of candidates, then you will like select that the correct output with really high probability. All right, so let's prove this. So let's fix data set X and so we want to understand the probability of the following set of outcomes. So let's define B sub t. So we're actually going to prove the statement in the white box first. So we're first going to prove that we don't see bad outcomes. And so what do we mean by bad outcomes? These are the set of y's such that the quality of y is less than the quality of the maximum quality of the best item minus best outcome minus 2 delta log d plus t. Okay. So notice I'm dropping the x everywhere. So we're only going to work with 1x for this proof. So I'm not going to keep on writing it in the score function, just to make the arithmetic more readable. All right. So we want to understand what's the probability. So we want to establish that the probability of y, our outcome landing in this set, we want that to be less than e to the minus t. Okay. So what we're going to do is we're going to compare this. Actually, before we do that. So notice that what can we say about the probability of elements that are in this bad set? Their probability is, again, this sort of like 1 over c, the normalizing constant, like for x, times times e to the epsilon over 2 delta times q max times this upper bound on the score. So it's like for the bad y's, the probability is at most this sort of messy expression. But it turns out this expression, we can simplify things a little bit, right? So this is, okay, so we get like 1 over cx up front. We get e to the epsilon over 2 delta q max. and then other things kind of multiply through. So then we get times e to the minus log of d, and then times e to the minus t. And this thing here, this is just like 1 over d, right? So we get 1 over c times 1 over d times e to the epsilon over 2 delta q max times e to the minus t. All right, so now let's try and understand the probability that y is in this bad set. Well, that's going to be strict. One way to get an upper bound on that thing is to take the probability of that y is in the bad set and divide it by something less than 1. We'll actually divide it by the probability that y is equal to the thing, something with maximum score. So we'll call, let's say, we'll take y max to be anything that maximizes the score for x. Okay, so now we can sort of plug in the upper bound we had up top. So we had 1 over c times 1 over d times e to the epsilon over 2 delta q max times e to the minus t. And on the bottom, we get 1 over c. The probability of this y max is 1 over c times e to the epsilon over 2 delta times q max. And so this cancels. This, oops, not that one. Sorry, actually, I made a mistake. I skipped a step. So let me go back and simplify this. So this is at most the size of the bad set times that thing I had before. So that was, 1 over c, 1 over d, e to the epsilon over 2 delta q max, and e to the minus t. And then on the bottom, what we have is what I wrote before, so e to the epsilon over 2 delta times q max. Sorry, so I'd lost the set size in the expression. Anyway, so now a few things cancel. So this 1 over c is cancel. The e to the epsilon over 2 delta q max, those cancel. And what we're left with is, the size of the bad set divided by d times e to the minus t. But the size of the size of the bad set, that's at most d. Okay, so this is at most e to the minus t because the bad set is like included in, is just like a set of there are only d possible outcomes. So the bad set is like has size less than d. Okay, so that is actually all she wrote. Like that's the complete proof. The what's going on here is because we're sampling things with probabilities that grow exponentially with the quality of the outcome, it takes like an exponentially large number of bad outcomes to swamp a good outcome. Okay, and so the chances that we see something that is more than like log of d worse than the optimum ends up being very small, because even if all the other things are like that bad, their probability won't add up to enough to like dominate the probability of one good outcome. One thing I'll mention is that sometimes we can improve. Sometimes we can improve our analysis when there are when there are like lots of good outcomes. So we might see I don't have an example of that in the lecture today because working those out tends to be a little on the messy side. But it's a good thing to keep in mind. So like, let's see, let's return to approval voting, right? So approval voting, we had D outcomes. What does this theorem say? It says that we find a candidate with score something like, Q max minus 2 log of D over epsilon, maybe plus 1. Okay, so in expectation, it's like this, and with high probability, it depends on how high a probability you want. Like, I guess one concrete thing we could say is that, say, with probability 2 log D plus log of 100, so that's log of 100D over epsilon. We get an outcome with score Q max minus 2 log D plus log of 100 over epsilon with probability at least like 99%. Okay, and so that's like a reasonably clean bound on just how bad things can get. Okay, because logarithms don't increase very quickly. And again, in contrast, if we'd used Laplace noise to release the number of votes for each candidate, we would have had much worse scores.